Hello, this is our narrated PowerPoint for, whoops, I don't know what just happened. Okay, this is our narrated PowerPoint for Chapter 7, which is all about the global wind patterns, circulation of the atmosphere. This is a fun chapter, and we will spend one of our class periods sitting together. Everybody will have a template that I will make copies of and hand to you, and together we will draw the global winds of the world. All right, so why does Earth have wind? Well, that's because Earth's surface is heated unequally, more so at the equator and less so at the poles. So not only do we have differences in temperature, differences in surface heat, but that leads to differences in pressure. So we have unequal pressure, and that is creating winds. Remember that air molecules always move from high pressure to low pressure, and that, of course, is called wind. So here in the lower 48 states, we are in a zone of winds known as the westerlies. So remember that winds are named for the direction from which they come. Okay, in other words, they are not named for where they are going. They are named for where they originate. So this explains why the majority of our weather patterns come to us from the west, okay? Because our winds in the long run are primarily blowing from west to east. And of course, this brings our weather patterns along. Now, yes, there are times that we get hit with tropical systems that have come in, from offshore, coming in from the east or maybe coming up from the south. In the short run, the winds can blow in any of 360 degrees, but in the long run, our winds are primarily blowing from west to east, thus the westerly. So we can distinguish between three different scales of circulation. You've got the micro scale, the meso scale, which of course is going to be in between, and then the macro scale. So micro scale winds are very small and localized. They do tend to be chaotic. They can last from just a few seconds to a few minutes. It could just simply be gusts of wind, downdrafts within a thunderstorm, or even dust devils. Okay, so mesoscale winds, these are larger than microscale, but usually they tend to be less than 62 miles across, and they can last from several minutes to a few hours. So some mesoscale winds, like thunderstorms and tornadoes, are also going to have a strong vertical component, meaning up and down movement within that storm or tornado. It's also going to include land breezes and sea breezes, which hopefully we will touch on in class, and then mountain and valley breezes. So macro scale winds are, of course, those are the largest wind patterns that we denote, and they tend to be on the planetary scale. So they're affecting very large portions of our planet, and they can be unchanged for weeks at a time. So a couple examples here are the westerlies, in which we live, and then also the trade winds. That day that we draw the global circulation patterns, we're going to learn about the northeast trades and the southeast trades. Now, there's a fourth scale referred to as synoptic scale, and that is just a smaller macro scale. So it's larger than mesoscale, but smaller than macro scale. That is synoptic scale. So these wind systems could be a good 1,000 kilometers in diameter, and these are going to include our mid-latitude cyclones and anticyclones. So the mid-latitude cyclones, we're going to learn all about those in Chapter 9, and those are our big weather producers here in the lower 48 states, and they're going to have a warm front and a cold front associated with them, and low pressure. And then the anticyclones are going to be our high pressure systems. And in general, these synoptic scale systems tend to move across the United States from west to east. And there's an even smaller macro scale denoted, and those are going to include our tropical storms and hurricanes. Okay, so global winds are a composite of motion on all the scales, micro, macro, synoptic, mesoscale. And of course, hurricanes, well, as I'm recording this, it is fall 2020. Yes, it's COVID, but it's also hurricane season and it's La Nina, so we expect to have ramped up activity in the Atlantic, and we do see that indeed. As a matter of fact, today, this is a Saturday, this is what, September 12th, I believe? Anyway, there are 6 tropical systems just between the Atlantic and the Gulf of Mexico. We're going to be keeping an eye on several of those. Okay, so what do hurricanes look like? Say on a satellite image, they appear as a large cloud moving slowly across the ocean. So it's basically this huge ensemble of thunderstorms. Okay, and of course the thunderstorms are mesoscale, and then the thunderstorms themselves within this much larger thing referred to as a hurricane, those thunderstorms are going to consist of numerous macro scale bursts, updrafts and downdrafts. So this is a pretty nice slide here to kind of tie it all together. So on the left there you have the lifespan of these winds. Along the bottom you have microscale, mesoscale, macro scale, kind of broken down into synoptic scale and planetary scale. And then you can see in there where your dust devils and microbursts lie, your tornadoes and thunderstorms, your land and sea breezes, the mountain valley breezes would be there as well on the mesoscale. Of course, your planetary scale winds are the westerlies, the trade winds, and the polar easterlies. Again, we will learn more about these actually later in this unit. And then, of course, at the synoptic scale, mid-latitude cyclones, anticyclones, and hurricanes. So this is what a dust devil looks like. So does it look like a tornado? Well, it does for sure, but they don't form in the same way, and they tend to not be quite so destructive. That being said, you might want to avoid just walking or driving into one if you can, but it would probably be relatively safe to stand where you are or sit in your car and film a dust devil. Okay, land breezes and sea breezes. So I do hope that we have time to cover this in class, but we may not, because it's alternate hybrid, and we only meet once a week. So let's begin over there on the left. We're going to set up a sea breeze in the daytime. So this kind of goes back to our discussion about the differential heating of land versus water. Remember that land is going to both heat up faster than water. It will also cool down faster than water. So in the daytime, you get a lot of intense heating on the land, and that air, the hot air, is going to rise. Okay, so you have low pressure over the land. Well, remember that water takes longer to heat up. Therefore, in the daytime, in your coastal areas, we expect the water to be cooler than the land. So you have higher pressure over the water just offshore and lower pressure on the land. So remember that air molecules always move from high pressure to low pressure. So the breeze here is moving from the water onto the land. And then you see there the full circulation going on there. That hot air is going to rise, but it's going to expand and cool adiabatically as it does. And then it's going to end up traveling back over top of the water and sinking. So that is referred to as a sea breeze. And for any other ex-bartenders out there, that is also a popular mixed drink. or rather it was popular in the 80s and 90s. All right, so over there on the right, the land breeze is what happens at night. So as the sun goes down, the land is going to cool pretty quickly, but that water is still going to hold on to its heat throughout the day. So at this point, I could ask if any of you have ever visited the beach, any beach. If so, have you noticed on a hot sunny day when you want to walk down to the water's edge and go for a swim, so you're going to leave your flip-flops back at your towel or chair. And as you're walking, boy, that sand is really hot on the bottoms of your feet. It kind of hurts. But then you get in the water and your feet feel better because the water's cooler. Well, at night, it's kind of opposite. At night, say, you're at the beach for the weekend with friends, and it's non-COVID times, and everybody goes to dinner, and then maybe afterwards you go and shoot a game of pool or sing karaoke or something fun and cheesy like that. And then you and your friends are walking on the beach at night. You take your shoes off. Guess what? The sand now feels really good. It's nice and cool. And then you go and put your feet in the water, and the water is actually going to feel warm. So what happens overnight is that you have lower pressure over the water because it's warmer, and the air molecules are going to rise and adiabatically expand and cool. And what do you have over the land? Well, you have cooler air, so it's more dense and it's sinking. Higher pressure. So higher pressure over the land now means that your breezes are going to blow from the land offshore to the water. That's referred to as a land breeze. So these two drawings here are what would typically happen in a 24-hour period down at the coasts, particularly on nice, hot, clear, sunny days. All right, so more on our sea breezes. The most intense sea breezes, meaning the strongest winds, are going to develop along tropical coasts that are adjacent to cool ocean currents. Okay, so why is that? Well, in your tropical locations, remember the tropics between 23.5 degrees north and 23.5 degrees south latitude, that's where you get your most intense solar radiation throughout the year. So we expect for the land to heat up more within the tropics. And if this tropical coastline is, say, on the west coast of North or South America, then it's going to be adjacent to a cooler water ocean current. And we talked about the ocean currents, I believe, in chapter 3. Anyway, so what's going to happen here is that you just set up the biggest difference between the pressure on land versus water. So you're going to have some really intense sea breezes and land breezes as well at night. Okay, valley breeze and mountain breeze, just very quickly, we're going to go through this. Okay, so we're going to begin on the left. Daytime heating. So you see here that you have mountains on either side and you have this nice valley in the middle. Perhaps an old river in the past has created this valley. Or perhaps this is a pull-apart basin somewhere out west in the Basin Range province. So during the day, you're going to get a lot of heating on those mountain slopes. So air above the mountain slopes is heated pretty quickly, and it's going to rise. So what we have here is what we refer to as a valley breeze, as in you're going to have the winds kind of blowing from the valley up the sides of the mountains. And then what do you have at say a higher altitude above the valley? You're now going to have sinking air, because as your air molecules are moving from the valley floor up the mountains on either side, you're now going to create lower pressure. So you're going to have cooler air above sinking down, air molecules moving towards the zone of lower pressure. Okay, how about on the right? At nighttime. Okay, so what's going to happen in night is that the air above the mountain slopes is actually going to cool quicker than the air down in the valley. So in the valley, you still have some of that, warmer air left over from your daytime heating and terrestrial re-radiation, and it's going to rise. So that's going to create lower pressure down in the valley, and then you've got this cooler air up on our mountain slopes, as they're going to cool more quickly than the valley, and that air is simply going to rush down the slopes on either side into the valley. So that is your mountain breeze. So in the daytime you have the valley breeze, and in the evening you have the mountain breeze. Okay, so the occurrence of a daytime upslope valley breeze can be identified by cloud development on mountain peaks. And occasionally this might progress to a mid-afternoon thunderstorm. So this kind of goes back to our lifting mechanisms, which we covered at the end of chapter 4. Remember orographic lifting? If there's a mountain range there, well, that is just the perfect lifting mechanism. And that air can rise, and then it will expand and cool adiabatically. It will hit the dew point temperature or below, and if there's some moisture content to it, then you're going to get condensation. You're going to form clouds, and perhaps you'll form a mid-afternoon thunderstorm if there's enough moisture in that air mass. Okay, Chinook winds, also referred to as, I think that's pronounced phone winds. I'm not exactly 100% sure on that. Maybe it's fern winds. Anyway, these are not going to be on your exam, but they are kind of neat, so we'll just discuss them very briefly. But again, they will not be on your second exam. So Chinook winds. These are warm, dry winds that sometimes move down the slopes of mountains. Okay, so as these winds move down the slope of mountains, they are warmed adiabatically because, the air molecules are being compressed. And then that air tends to be dry because these Chinook winds are only going to happen on the leeward side of a mountain range. Okay, so these winds that are warm, potentially hot, and dry can bring drastic changes in temperature to the leeward side of a mountain range. So if it's winter or spring and you have some snow cover, well, that snow might melt very rapidly. So actually, Chinook is a Native American word that means snow eater. And then they have these in Europe as well, but they have a different name for them. That's where they refer to them as phone. This is just a drawing. I have to assume, well, I know that we have two different examples going on here. I was going to say I assume this is the Rocky Mountains, and the Rocky Mountains is a good example of this, but so are the mountains in California. You've got the Coast Ranges, you've got the Sierra Nevada mountain ranges. So in California, these Chinook winds are referred to as Santa Ana winds, and that name might sound familiar. You've probably heard them talking about Santa Ana winds occasionally, either on the Weather Channel or on the news. If you happen to have dry vegetation and fires are easily forming, and then if that happens to be at the time of year that you get Santa Ana winds, well, that's very bad because the Santa Ana winds just kind of help fuel those fires, unfortunately. So another example of these are warm, dry Chinook winds, sometimes moving down the east slope of the Rockies. And again, if this is, say, winter or spring and you have some snow cover there east of the Rockies, well, that snow might very easily quickly melt because of the warm, dry Chinook wind. Okay, so this is a nice little drawing here of the Santa Ana winds. And I love that they're showing you the direction. Oh, I forgot all about the San Gabriels and the San Bernardino Mountains. So many mountain ranges in California. Anyway, so on the eastern side of the Sierra Nevadas, the leeward side of the Sierra Nevadas, you have the Great Basin. And why have they drawn it to look like a desert? Because it basically is. It's a rain shadow desert. Anyway, okay, so let's read through this quickly. This is important. Yeah, this is probably going to be an hour-long chapter. That's okay. The Santa Ana is a hot, dry, dusty wind in southwestern California that blows westward through canyons and passes towards coastal areas during spring and late fall. So it has its origin in the relatively stable high-pressure system that exists in the Great Basin. It's referred to as the Great Basin High. So it often exists over southern Idaho, Utah, Nevada, and eastern California. Anyway, so the Great Basin High is characterized by a slow but giant clockwise, because it's an anticyclone, high pressure, clockwise flow of air that is prevented from expanding eastward by the Rockies, prevented from expanding westward by the Sierra Nevadas. Now, how do you set up the Santa Ana winds? Because you pretty much have that Great Basin High, I think, really all year long. So if you have a low pressure system in the Pacific off the California coast moving into Southern California, well, then you have a low pressure system sitting there, and you've got, this high pressure to the east. So those air molecules are going to move from the high pressure, from the Great Basin High, through the canyons and mountain passes there and into Southern California. So pretty neat stuff there. And the name Santa Ana winds, those were named by early settlers near a town that was called Santa Ana, California. All right, so, golly, as I'm recording this for fall 2020, there are, I believe, at least 100 fires that are burning out west. And yes, California has a lot of them, but they're also really bad in Oregon and Washington and Idaho and several states out there. It's just really, it's not a good time to live out west. And of course, all the experts are saying, yeah, this is climate change. Right now, they're saying this is the worst fire season that we've ever had, and we've had more fires and more acreage burned at this point in the year than we've ever seen before. And conditions out there are just very hot and dry and just ready for anything like a lightning strike or a gender reveal party, unfortunately, or down power lines to set up fires. But these are just some images here. You have your map up on the top left showing, air moving from high pressure to lower pressure through those mountain passes in Southern California. And then you see a satellite image there on the bottom left of smoke from wildfires and the direction it's blowing due to the Santa Ana winds. And again, the Santa Ana winds, they just exacerbate the wildfires. Now, right now, what's these fires that are occurring in the western states right now in September 2020, those are more to the north. I don't know that we have these Santa Ana winds very strong at this time. Okay, local winds, these are not going to be on your exam. We will just very briefly discuss them. So katabatic winds, also known as fall winds, originate when cold, dense air begins to move. Of course, this is going to occur in areas adjacent to highlands, where you might have some cold, dense air forming. So better known katabatic winds may have local names, such as in the French Alps, they have winds that will blow from your higher elevations in the French Alps, where you might have glaciers, down to the Mediterranean. These are referred to as maestral winds. We also get these katabatic winds blowing off Greenland and Antarctica. Greenland, by the way, is actually mostly covered in snow and ice. So not to be confused with Iceland. Iceland doesn't have nearly as much snow and ice as Greenland does. And of course, Antarctica, everybody knows it's a continent and it's covered in glaciers. And you can get some pretty significant differences in temperature here, which is how you can set up these katabatic winds. Country breezes are another type of local winds, also not on your exam. These are mesoscale winds, and it's going to have to do with the urban heat island effect, so caused by the uneven heating of urban versus country areas. And this results in the flow from country to urban areas. Why? Because your urban areas, remember the urban heat island effect? We discussed this in a previous chapter. And you're going to have higher temperatures. So you're going to have air that's lifting, and you're going to set up lower pressure in the urban area, slightly higher pressure on the surrounding countryside. So your winds are going to blow from the countryside into the city. So this is a drawing. Okay, the drawing on the bottom left isn't fabulous, but the map over there on the right is pretty good. That's showing Greenland and how you can set up these katabatic winds. Here's an image of maestral winds. All right. Do cities produce their own local winds? And the answer is yes, especially large cities with a lot of, blacktop parking lots, a lot of just pavement in general, and you're going to get a very strong urban heat island effect. So there's a drawing there just showing how the country breeze is set up. So you simply have lower pressure over the urban area because it's warmer, and then the air molecules are going to move from the higher pressure outside of the city into the lower pressure within the city. Okay, so the Hadley cells. All right, so yes, this is going to be a long chapter. I probably should have started about an hour sooner. That's okay. Anyway, we're going to now start to learn about the macro scale winds. It's actually really a lot of fun. And again, in class together, I hope everybody will come to class that week, whichever day you're supposed to be there, so we can draw these things together. It makes it so much easier to learn and remember this stuff. All right, so there in the top left, you're looking at a simple circulation model if the Earth did not turn. Well, that's just kind of silly because guess what? The Earth does indeed turn. Okay, so yes, do we have warmer air around the equator rising and then moving north and south and then sinking back down at various locations like 30 degrees latitude and 60 degrees latitude? Sure, we do. But the Earth also spins, so that we are going to set up these very distinct wind zones. There's going to be 6 of them, 3 in the northern hemisphere, 3 in the southern hemisphere, with nearly identical names. All right, so this is our 3-cell global circulation model. Really 6 cells. There's 3 in each hemisphere. You'll notice some names on here that I may have mentioned before: westerlies, northeast trade winds, polar easterlies we haven't really talked about yet. So the cells that run from the equator to either 30 degrees north or 30 degrees south, those are referred to as Hadley cells, named after a researcher that discovered them, studied them. And then from 30 degrees to 60 degrees, you're going to have Ferrel cells. And then from 60 to 90, you're going to have polar cells. And you're going to see this in both hemispheres. Okay, so this global circulation pattern was first proposed back in the 1920s. Warm air rising at the equator. And then it's going to move north and south from the equator. So it's rising and then it's moving north and south at higher altitudes within the troposphere. Well, it's going to cool along its journey upwards, adiabatic cooling, and simply as it's leaving the tropics, it's going to cool enough that it's going to sink back at between 20 and 35 degrees latitude, or we could just say 30 degrees. That's what we're going to use when we draw the wind cells together as a group. Okay, so the trade winds are going to meet at the equator in a region that's going to have a very weak pressure gradient, is going to be referred to as the doldrums. And maybe you've heard that term before. So commonly, doldrums is used to describe perhaps a mood that you're in, as in you're kind of melancholy, you're just kind of down, maybe you don't really have any reason to be down, and yet you are anyway. We might refer to that as the doldrums, but what it really means in atmospheric science is that you don't have strong winds here. So the doldrums were not very good for sailing ships back before we had motors on these ships. So the westerly circulation of surface winds between 30 and 60 degrees latitude lies within something called the Ferrel cell. And of course, this band of wind is known as the westerlies or prevailing westerlies. Now, circulation between 60 and 90 degrees occurs within something called a polar cell, and that's going to produce something referred to as the polar easterlies. as in winds that are coming from the east, and they are moving towards the poles. I'm sorry, they're moving towards the equator. All right, so some idealized pressure belts. So pressure zones drive winds, of course, as in differences in pressure drive winds. So we're going to discuss the ITCZ and the subtropical highs. Okay, so around the equator, you have generally low pressure because you have warm air that's rising. So the equatorial low that this sets up is also referred to as the Intertropical Convergence Zone, or the ITCZ for short. And the ITCZ tends to migrate with the seasons. So fall and spring, it tends to be clustered about the equator. Summer, it moves slightly further north into the northern hemisphere. Winter, it moves slightly further south into the southern hemisphere. And we tend to find rainforest and moist conditions within the ITCZ. Now, subtropical highs are relatively permanent high pressure zones that occur in belts sort of between 20 and 35 degrees latitude, either north or south, either side of the equator. And what do we tend to find at our subtropical highs? Well, we find deserts because we have dense sinking air that is quite dry, and then as that air is sinking, it's going to warm adiabatically. So you get warm, dry conditions, and that's what we expect of the world's great deserts like the Sahara. Now, the polar high pressures near the Earth poles are where the polar easterlies originate. And in case I forget to mention this in class, the poles, both the North and South Pole, are frozen deserts. So you look at images from the poles and you see all this snow and ice and you think, how can that be a desert? I see past precipitation and there's no sand there. But even though there has been precipitation in the past, there's not a whole lot of it. It's just that it tends to, not go away. So in class, we are going to diagram and explain the three-cell model of the general of Earth's atmosphere. So this image here is very important in the summers when I teach this class fully online. Okay, it's also going to be important for any of you that are on quarantine or having other issues and cannot make it to class the week that we draw this. I really recommend everybody come to class the week we draw this because this is very important. So we'll just take a very quick shot at trying to narrate this. It's going to be very quick because I expect people to come to class and we're going to do it together, and we will, of course, spend more time discussing why this happens. So it's going to begin at the equator where you have warm rising air, and as you look over there on the right, you see the arrows moving up. Warm air is rising, and then it's going to head north and south in what we call these Hadley cells, and this is higher in the troposphere, and it's cooling as it's moving, and then it's going to sink back down at 30 degrees north and 30 degrees south latitude. Okay, so there around the equator, it's right in the center of the tropics. Your ITCZ hangs out there more of the year than other places. This is where you're going to find equatorial low pressure because you have warm rising air. This is where you're going to find rainforest. This is also where you're going to find the doldrums, or places where the winds are just not that strong. So let's go up to 30 degrees north. So from now on, we will primarily focus on the northern hemisphere here. So at 30 degrees north latitude, the winds are going to sink back down. Okay, so that's going to give you a subtropical high, as in high pressure. You're going to tend to find deserts there. You're going to find something called the horse latitudes. There's a really sad story about the horse latitudes. All I'm going to tell you is that sailing ships sometimes would get stuck in the horse latitudes, and the winds would leave for many days at a time, and the ship couldn't go anywhere. Anyway, so this air sinking back down at 30 degrees is then going to head north or south. Okay, so it's going to head, and we're going to go ahead and move north. So that wind is going to head north, but it's going to be turned or in apparent deflection to the right because of the Coriolis effect. Okay, so here between 30 and 60 degrees north latitude, we have the westerlies. So they're really coming from the southwest. We just refer to them as the westerlies. And this is where the United States sits, and this is where we have a lot of mid-latitude cyclones, as we constantly have moving across the United States. Now, also at 30 degrees north, as that air is sinking, it's also going to head back down south. But it's going to have an apparent deflection to the right, which looks as if it's moving to the left from our drawing. Why the discrepancy? Well, we'll talk about that in class. And that's why you have the dashed arrows there in addition to solid arrows. Anyway, from 0 to 30 degrees, you have your northeast trade winds. Notice they're coming from the northeast. Why called trade winds? Because sailors could very much rely on these winds to get them where they needed to go to, negotiate to buy spices or whatever they were going to bring back to Europe. All right, so now let's go up to 60 degrees north latitude. You're going to have this weird subpolar low, and you're going to have air that is warmer than what's around it, so it's actually going to rise, and that's going to set up your polar cell between 60 and 90. By the way, taking another look at the 30 to 60 degrees, that of course again is known as a feral cell. Okay, so back to 60 degrees. You have this subpolar low, and air is going to rise, and it's going to head towards the North Pole and then sink back down. So this air moving from the North Pole south, again, it'll have an apparent deflection to the right due to the Coriolis effect, which looks to us like a left-moving arrow, and is coming from the northeast, and we simply refer to these things as the easterlies or polar easterlies. All right, and also between 60 and 90 degrees north latitude is something we can refer to as the polar high, or a permanent high pressure system. Okay, anything else we need to take a look at here? We'll briefly look at the southern hemisphere. So between 30 degrees south and the equator, you're going to have these winds that blow from the southeast. We refer to those as the southeast trade winds. You're going to have another subtropical high and deserts as well, another set of horse latitudes. If you look between 30 and 60 degrees south latitude, you'll have another set of westerlies. This time they're coming from the northwest, but it's westerlies nonetheless. All right, I think that's enough for attempting to explain this on the PowerPoint. We will get a much better understanding when we draw these together from scratch in class. This is just another image from a textbook of our 3-cell model. Not the best image. Okay, why westerlies? Remember that air pressure decreases more rapidly with altitude in a cold air mass than in a warm air mass, as the air molecules in the cold air mass are more concentrated at lower altitudes, because it's sinking air if it's cold. Okay, so this creates higher pressure in higher altitudes at the equator, as in the mountains, and lower pressure with lower altitudes, lower pressure with altitude at the poles. Okay, so this creates something called geostrophic airflow from the equator towards the poles, and then the Coriolis effect deflects it towards the right. Okay, I will go ahead and tell you that you can forget about that last bullet there. We briefly may have touched on geostrophic airflow in a past chapter, and I'd mentioned that it would not be on your exam, and you're not going to need to know that. Why westerlies? We will answer that question in class together when we draw the global backer scale winds. This is a very simplified map here. It's showing that actually we're going to skip this. Let's just completely skip this, because I think this is just going to confuse us, and this involves geostrophic winds, which we are not going to touch in this semester. Okay, so we are going to come back to this one. Just very quickly, just know that, do they have any kind of latitude there? I guess that red arrow is kind of between maybe 30 degrees north and 50 degrees north. So winds in general want to move from a warmer location to a colder location. So the pressure gradient force might try to take those winds north. But Earth is turning. We do rotate. So the Coriolis force wants to deflect those winds to the right, which in this drawing is a full 180 degrees away. But you set up kind of a balance between the pressure gradient force and the Coriolis force, and you end up with your winds moving from west to east. And this is likely happening for the most part between 30 and 60 degrees north latitude, but also south latitude, setting up westerly. Okay, so this is just another, this is actually a pretty good little drawing here. Another way to show the three-cell model. Now, what they don't have is the arrows showing the direction of wind movement. That's okay. We have it on a previous diagram, and we'll talk about it in class together. But what's kind of neat about this is it's giving you a little bit of description there on what kind of climate are you going to have, like equatorial low ITCZ, abundant precipitation in all seasons, and warm and low pressure. Subtropical highs, dry in all seasons. Within your westerlies, dry summers, wet winters. There's a little something there about the subpolar low. The polar front is something that we will discuss briefly again in Chapter 9 when we talk about our mid-latitude cyclones and how they form roughly or close to 60 degrees north latitude along the polar front. So you have some images there of our sailing ships relying on the trade winds and the prevailing westerlies. You have a picture there of the doldrums around the equator, and then unfortunately you have a picture there of why the horse latitudes are referred to as the horse latitudes, and it has to do with the ships getting stuck and not being able to move, and they're going to run out of water. Okay, sorry about that. I just wanted to see if they might show us our semi-permanent pressure systems in the summer, and maybe we're going to have a slide for that coming up. Okay, so what we're looking at here in this slide, basically this is a repeat of something we looked at before. So we're going to move on. You always can stop these and pause and read through them more on your own. Okay, so on this slide here, just again, we've already talked about most of this, the ITCZ, the subtropical highs. Here again, they discuss the horse latitude a little bit more. And this is a very simplified drawing showing our global wind patterns, the westerlies, trades, the polar easterlies there on the left, and then some of your semi-permanent highs and lows on the right. Okay, so here, this is just another way to kind of show this. Again, they're focusing just from 60 to 90 here, and they have left off the arrows showing you the direction of wind movement, but that's okay. Here they're kind of focusing on what's happening in a vertical sense. Okay, so air rising at the equatorial low, forming a Hadley cell as it sinks back down at the subtropical high, giving you deserts like the Sonoran Desert in the desert southwest of the United States. Setting up your ferrule cell there and having air rising at about 60 degrees along the polar front. Okay, so this is kind of a neat image here. So just looking at the amount of rainfall that's occurring, mapping that out in a satellite image, you can clearly see the ITCZ. So the equator is shown there along with 30 degrees north and south, just to give you an idea, where does that 30-degree line hit? Well, it kind of hits pretty close to the Florida-Georgia border, just so you know. All right, so the ITCZ, again, is really easy to pick out here because of all the red and orange. And notice that it's sitting slightly north of the equator, so this should this image should have been taken during summer in the Northern Hemisphere. And this is another neat view of the ITCZ. In this case, it is just simply a satellite image looking at the cloud cover. All right, so you see that line going across that is labeled ITCZ. And it's pretty close to the equator. I want to say, let's try to, if this was they've turned this globe to where we could see North and South America, it would be a little bit easier to see that. But say, for example, the Tropic of Cancer is right about Havana, Cuba. So in this image, the ITCZ is pretty close to the equator, so this is very likely going to be in spring or fall. Here we go. All right, now finally, we're going to compare the high and low pressures of winter to summer as well. So you see there that they're not exactly the same. We talked about the winter pattern on a previous slide. So the slide on the bottom there, for summer in the Northern Hemisphere, we have this thing called the Bermuda High. And the Bermuda High sometimes can help to steer hurricanes. And of course, sometimes you might have a high pressure system, an anticyclone moving west to east across the United States that can also help to steer hurricanes. Okay, monsoons. Oh, monsoons, I forgot they were in this chapter. It's actually, monsoons are kind of fun to learn about. So probably everybody has heard the term monsoon, and you just assume that it's very heavy rainfall for, well, perhaps weeks or months at a time. And the answer is yes, that is true. But what is not as well known is that there's also a dry monsoon. So what monsoon by itself really means is a seasonal reversal of winds happening twice each year. Okay, so the most famous monsoon is the Asian monsoon, which affects India, China, Korea, Japan, Southeast Asia. So the monsoon is driven by pressure differences due to temperature differences between land and water, between the oceans and the continents of India and Asia. So this goes back to the differential heating of land versus water. There's a wet monsoon in the summer months and a dry monsoon in the winter months. Why does this occur? Well, we should have a map coming up on the next slide, and we'll discuss it there. So the wet monsoon occurs when warm, moist air from the Indian and Pacific Oceans moves across to East Asia in the summer. Yay, we do indeed have a map, and we've got winter and summer. So let's focus on summer first. I think we might have seen, no, this looks very similar to an image where we were looking at Myanmar back in chapter 3, I believe. Okay, so you're looking at the Indian Ocean. You got the Pacific Ocean over there to the right. You've got India. You've got China. Japan is kind of, and other parts of Southeast Asia are kind of hidden by the graph that's superimposed there. So what happens in the summer is that the land is going to heat up much quicker and to more of a degree than the water. So you end up with warm rising air over the land, which creates low pressure. And the oceans are cooler than the land during the summer. So you simply have higher pressure over the ocean, lower pressure over the land. So for several months, you're going to have winds moving from the ocean onto the land. And of course, that air moving in is very moist. So take a look at that graph down there on the bottom right. And they're going to split, the winter is on two different ends, and your warmer months, say June, July, August, September, are there in the middle. So you see that you get a ton of rainfall basically May through October, and that is your wet monsoon. And then in your colder months, you get a lot less rainfall. Why? Now look at the one to the left, the winter monsoon. In the winter time, the land is going to be colder than the water. So you have high pressure over the land and lower pressure over the water. In the winter months, the cooler months, the winds are going to blow from the land off to the water. So you're just not bringing in moisture anymore. So these people don't just have, you know, average precipitation throughout the year like we might expect to have in the United States. They have a heck of a lot of precipitation in the summer monsoon and then almost no precipitation during the winter dry monsoon. Now, I'm sure this is an exam question or an extra credit question. Does North America have a monsoon? The answer is yes, although you don't necessarily hear a lot about it, I guess, unless you live down in that area. So this occurs in the southwestern US and northwestern Mexico. So this is going to happen in the summer. Of course, it's driven by extreme temperature differences, which creates pressure differences. So what you have is intense heating of the desert southwest, warm rising air, so you get low pressure over Arizona and the rest of the desert southwest, and then you have cooler waters and therefore higher pressures from the Gulf of Mexico and to some extent the Gulf of California. Anyway, well, I'm sorry, let me reverse that. More so from the Gulf of California, but also from the Gulf of Mexico, but to a lesser degree. So basically, you're going to have winds moving from the higher pressure over the water into the lower pressure area of the desert. So it's called Desert Southwest because, well, it is an arid region, but they do have their rainy season. They do have a summer wet monsoon. And this is kind of neat. So not only do we have a map there showing this low and moist air coming from the Gulf of California, the Pacific, and the Gulf of Mexico, you see an image there of wherever Arizona and the saguaro cacti there. It looks very different from North Carolina, doesn't it? And then on the graph on the far left, you see the rainfall throughout the year. So July, August, September, October, you're going to get the majority of your rainfall. And you're going to get less in the other months. Now, I might ask a question. Do the seasonal differences in rainfall in Arizona, are they quite as pronounced as the seasonal differences in rainfall in Southeast Asia? No, they are not. Just not quite as big a difference here. Okay, jet streams. I forgot jet streams were in this unit. Okay, so jet streams are upper level airflows. So they're higher up within the troposphere. Upper troposphere winds, they tend to be embedded in the westerlies at these higher altitudes. And they tend to be kind of skinny. The width of jet streams is from less than 100 kilometers to more than 500 kilometers. But they're relatively skinny. They're basically like these fast-moving rivers of air at higher altitudes in the troposphere. How fast? 100 to 400 kilometers per hour. That's pretty darn fast. And we have two types of jet streams. We have the polar jet stream, which we're more likely to hear about in the majority of the United States. And then there's also a subtropical jet stream that really only the very southern states are going to experience. Southern portion of the southern states. Okay, so the polar jet stream exists along the polar front. In other words, it's kind of forming roughly close to about 60 degrees north latitudes. And the polar front is a clash between cold winds of the polar easterlies and the warmer air of the westerlies. So this is kind of just a neat image here showing the jet stream. By the way, these big undulations in the jet stream, those are referred to as Rossby waves. So here you see the jet stream dipping down into, well, Canada for sure, and maybe very little of the United States. So this tells me that this image is representing summer for the most part. We tend to find the jet stream not dipping as far south in the United States in the summer as in the winter. Okay, so in this image here, we're just being reminded that there are two basic types of jet streams, the polar jet and the subtropical jet. Living where we do or regions further north, you're likely to grow up hearing about the jet stream dipping down, and it's just the polar jet stream that they're talking about. But there is a subtropical jet stream, and it tends to affect, say, Southern California, Mexico, maybe the desert Southwest occasionally, perhaps coming across Florida occasionally. So this is a neat image here because it's showing you the expected placement of the polar jet stream both in summer and in winter. So in summer it tends to hang out further north because the warm moist air mass is coming in from the Gulf. Well, they're powerful and they're kind of keeping that polar jet stream further north. What we might like to have happen in the summer is to have the polar jet stream move south and bring us some relief. It just doesn't happen often, and it doesn't come as far south as we would like it to. Now, in the wintertime, when we don't necessarily want cold, dry air coming down from Canada, the polar jet stream tends to dip sometimes pretty far south in the wintertime because well, the moist, warm air coming from the Gulf of Mexico in the winter is just not quite that strong. Okay, so the polar jet stream is the most prevalent of the two jet streams. In other words, more prevalent than the subpolar jet. And it basically is going to form or occur along the polar front, as we discussed on a previous slide. The jet stream also tends to move faster in winter because you have a stronger temperature gradient. And in the winter, again, it occasionally moves from north to south. And in general, throughout the year on its journey, it's going to migrate between about 30 and 70 degrees north, and it's going to affect weather in the mid-latitudes all year. So the subtropical jet, so this one's not as prevalent, but it is a semi-permanent jet stream over the subtropics. It is oriented west to east, centered at around 25 degrees north in latitude. And again, both of these jet streams also occur in the southern hemisphere. We're just going to focus on the northern hemisphere. So the subtropical jet is mainly a wintertime phenomenon. It tends to move slower than the polar jet stream. In the winter, it may occasionally sweep northward, bringing warm, humid conditions to the Gulf Coast. All right, so basically what do these jet streams do? Well, they tend to try to help correct for the heat imbalance that we have on this planet. Okay, so as we get these big undulating waves, also referred to as Rossby waves, these meanders help to distribute cold air from the north to the south. This is just a drawing of the polar jet stream. Okay, so the subtropical jet stream here, is this the thing they refer to as the Pineapple Express? It might be. We might see that in an upcoming slide. So again, this is a semi-permanent jet stream. It's not quite as permanent as the polar jet stream. The subtropical jet stream is more prevalent in the winter. And again, it moves slower. But here we have a nice satellite image showing it bringing moisture to Mexico, Central America, parts of Texas. Looks like it's going to skim the Gulf Coast and move across Florida. Okay, we have seen this same image before back in chapter 3. So these surface currents in the ocean are related to the global winds. Okay, so as the winds of the world begin to blow in reaction to temperature differences and therefore pressure differences, and they are also deflected to the right in the northern hemisphere due to the Coriolis effect, they pass over oceans and drag these waters with them. So the interaction creates our warm and cold ocean surface currents, which help to equalize temperatures across the planet's surface. Okay, so the Coriolis effect, gosh, in which chapter are we first going to encounter that? That's a good question. It might have been in the chapter 6. Anyway, so the Coriolis effect, I will endeavor to, well, we will discuss it when the day that we draw the global wind patterns. But basically, the Coriolis force, or Coriolis effect, occurs because Earth does turn, and this gives an apparent deflection to the right in the northern hemisphere and an apparent deflection to the left in the southern hemisphere. So it tends to deflect surface currents, the warmer currents, towards the poles, which form nearly circular patterns of ocean currents referred to as gyres. So look there in the Atlantic Ocean, North and South Basin. You have the North Atlantic Gyre and the South Atlantic Gyre. So these are basically in the northern hemisphere, the gyres are slowly rotating clockwise or opposite of our hurricanes and tropical storms. So the Gulf Stream is strengthened by westerly winds and continues northeastward, where it becomes the North Atlantic Drift, and it therefore brings milder temperatures to Western Europe. So unfortunately, these gyres, they're these big, huge rotating surface currents in our ocean basins. They collect garbage, and the North Pacific Gyre is especially bad. It's basically referred to as a big floating garbage patch, unfortunately. Anyway, and then last on this slide, going to something that we did discuss in a previous semester when we first looked at this diagram. Previous semester, I'm at previous chapter, chapter 3, when we first looked at this diagram. Notice that the East Coast has a warm water current and the West Coast has a cold water current. So in August, water temperatures on the East Coast could easily be 70 degrees Fahrenheit. Hey, who are they kidding? I've been in the waters at Wrightsville Beach where it was more like 80 degrees. Just so you know, some of you have experienced that for yourself. But on the West Coast, that ocean temperature could easily be 10 degrees colder, because on the West Coast, you're right up against the California current, which is a cold water current. Remember, we said before that in an ocean basin, the current on the western margin is warm and the current on the eastern margin is cool. And here's just kind of zooming in on that and talking a little bit more about the North Atlantic Drift. So ocean currents account for about 1/4 of the Earth's correction for that heat imbalance, and the other 3/4 is due to the winds. Okay, so just a little something in addition here on ocean currents and how they can affect the climate in certain areas, and again, trying to correct for Earth's heat imbalance. So if you have a cold current offshore, like you would have on the West Coast where you have the cold California current, that is going to give you a drier climate than if you had a warm water offshore current. So, for example, on the East Coast, you have the Gulf Stream, which is a warm water current. You're going to have a more moist climate on the eastern seaboard and a more dry climate over on the West Coast. And indeed, that is true. Okay, yes, you do have some rainy areas in the Pacific Northwest, Northern California, Oregon, Washington, but that's because you have mountains and the orographic lifting. But in general, if we were to look at, say, Southern California versus the East Coast of, say, Georgia and the Carolinas, well, yeah, it's more dry out there in California. Okay, ocean currents and upwelling. Oh, that means we're getting ready to talk about El Nino and La Nina. Yeah, I should have started recording this an hour sooner than I did. Okay, so ocean currents and upwelling. Upwelling is a wind-induced vertical movement, basically the rising of cold water from deeper parts of the ocean rising up to replace warmer surface water. Okay, so upwelling occurs where the winds blow parallel to the coast towards the equator. So we expect to have upwelling off the west coast of South America. So the Coriolis effect deflects it away from the coast, basically taking surface water away from the coast. So you then get it replaced with this cold water upwelling. And this is important because cold water upwelling brings nutrients from the deep up to the surface, which is great for the fisheries. Okay, so in normal conditions or La Nina conditions, the Peru current offshore the west coast of South America is an example where you find upwelling, as is the California current, west coast of United States. California current brings upwelling, and you should also get upwelling on the west coast of Africa. But there's this thing called El Nino that we get from time to time that attempts to shut this down. Okay, so El Nino and La Nina, I think you'll have 1 or 2 questions on each of these on your second exam. Also, it helps to go to the NOAA website, NOAA, and type in a search and do a little reading of your own on El Nino versus La Nina. So El Nino is a relaxing of the trade winds, which means that this movement of water from, say, the Western Pacific off the west coast of South America, moving west towards Asia, that kind of shuts down. So you get a gradual warming of the Eastern Pacific waters in December or January because the trade winds have relaxed. It happens roughly every 2 to 7 years and lasts for anywhere from 9 months to 2 years. And El Nino will shut down this cold water upwelling. It also does some other things we'll talk about on another slide. La Nina is the opposite of El Nino. La Nina is basically normal conditions amplified. So it refers to a strengthening of the trade winds, and you have your waters carried from the west coast of South America westward over towards Asia, and you have even greater cold water upwelling. So producing an equatorial current away from South America towards Australia and Indonesia. These are really nice drawings. So El Nino's on the bottom. We'll start with that one there. So again, it's a weakening of the trade winds, a response to a fall in pressure over the Eastern Pacific with a corresponding rise in pressure over the Western Pacific. Okay, so every El Nino causes a pressure drop in the Eastern Pacific and a rise in the pressure of the Western Pacific. So what happens here is that you shut off the trade winds, so you don't have warm waters leaving South America heading towards Asia. So you're going to shut off that cold water upwelling. So this is bad for fisheries. Okay, so up in the top image there, that's La Nina, the opposite. So you have a strengthening of the trade winds. You have a strong equatorial current moving from the west coast of South America over towards Asia. So you have strong cold water upwelling and that strong Peru current. So what does this mean for conditions, say, in South America or North America? So these are very useful websites that you can go to on your own, and when we're in class together, we normally go to these websites and we look at it together. We're not going to have time for that with the alternate hybrid, but I recommend going to these websites here, part of NOAA, and reading about El Nino and La Nina. Okay, so here we go. Effects of El Nino. All right, so it is most catastrophic for Chile, which is that long, skinny country on the west coast of South America, Peru, Australia, and other countries. So what happens during El Nino years is that arid regions can get a lot of precipitation, which is not necessarily a good thing. A change in surface water killing fish. The cold water upwelling along South America's west coast is shut down, bad for fisheries. How about the United States? Warmer winters in the north central U.S., wetter winters in the southwest U.S., colder and wetter winters in the southern U.S. Most importantly, when you have El Nino, you have a relaxed hurricane activity in the Atlantic. By the way, El Nino and La Nina together are also referred to as southern oscillation. Okay, so sometimes it's referred to as ENSO, E-N-S-O. Okay, how about La Nina? Okay, so La Nina is the opposite of El Nino. By the way, as we record this in September of 2020, we are in a La Nina event, although they think it's pretty weak. So La Nina in the Western Pacific, you're going to have wetter than normal conditions occurring. The problem with La Nina for the United States is more frequent hurricanes in the Atlantic, and well, we're in the height of hurricane season right now. You also expect to get cooler, wetter winters in the northwest U.S., cold winters in the northern plains, warm winters in the southwest and southeast U.S. So we might expect warmer winter here in North Carolina in 2020 because of La Nina. And then taken together, southern oscillation is the seesaw pattern as an atmospheric pressure between the eastern and western Pacific. So when you put all this stuff together, it's called El Nino southern oscillation, or ENSO, E-N-S-O. So this is really some neat images here showing, well, El Nino in the winter, top panel. Next panel down, El Nino in the summer. Next panel down, La Nina in the winter. Next panel down, La Nina in the summer. Just to kind of give you an idea of different parts of the globe, how they're going to be affected. We are going to skip this slide. I wonder if the strong El Nino of 97 is listed. I think it is. One thing I'm going to point out here is, well, look on the bottom, try to imagine where 1997 is, and then go up into the top where you have the red. So the red is your warm El Nino phase, and back in 1997 was a very strong El Nino. Of course, it lasted. It wasn't necessarily just 1 year. Remember that these things can last up to 2 years. This is a neat image here. So, speaking of El Nino in 1997, that was a very pronounced El Nino year. And you see there the incredibly warm waters hanging out off the west coast of South America. They're not supposed to be there, but because the trade winds weakened, you had a strong El Nino then. And then to converse that with the La Nina that followed that El Nino, and this was in December of 2000, you have very cold waters off the west coast of South America. You can pause here and take a look if you would like to. Is this all 97? It is. Okay, that's kind of neat. I'm not sure that they're really showing us what the colors mean. Okay, white and red areas are warmer water. So not just red as you would expect, but the white is warmer waters. So again, just kind of showing how pronounced the El Nino event was in 97, and it spilled over into 1998. This we have seen before. We can skip this here. This is basically the Bermuda High. We discussed that previously. We can skip this one again. This is a repeat. We've seen this. We should be about at the end, and I hope so, because it's going to take forever for this to save. All right, so in general here, you're looking at different parts of the globe, and I'm assuming these are your average annual precipitation, both in inches and centimeters, and it's color-coded. So more precipitation where you have blues, less precipitation where you have, say, tan and, well, dark tan and light tan. So are there patterns here? There are. Let's look at Africa first. Can you clearly find the Sahara Desert? Yeah, you can. So it's right there, kind of clustered around between, say, 20 and 35 degrees north latitude, which is where we expect to find the world's major deserts. It's also, part of the reason it's so big is because that's a pretty big continent there, Africa, especially that northern half of it. Notice the United States. Notice that in general we have more precipitation on the eastern seaboard and the Gulf states, and kind of moving up into part of the Midwest there, where you can have the influence of warm, moist air coming in from the Atlantic Ocean or the Gulf of Mexico. And the West Coast is generally drier, except for the mountains. South America, wow. Well, we know there are rainforests in South America, right? And you can clearly see that where you see your areas there within the tropics and all the moisture that you're going to have throughout the year. And then let's look over there at Southeast Asia. And of course, India and Southeast Asia having their monsoon, wet and dry, but we might say that the wet monsoon far outdoes the dry monsoon. And in general, they have a lot of precipitation throughout the year. And here we're basically looking at the difference between winter and summer and how your zones of precipitation can shift seasonally. So regions with high pressure will be dry, regions with low pressure will have ample rainfall, warm areas will have more rain than dry areas, and continental interiors will be drier. Okay, question. Is it January or July? Okay, so clearly both images show the continent of Africa, and we need to figure out which is which. Do we see the equator here? Yes, we do, kind of cutting through the middle there of Africa. Okay, so which of these would be July, looking at the rainfall? If you said block A on the left, you'd be correct, as in north of the equator. And January is going to be block B on the right, where you have your greater precipitation and therefore greater temperatures south of the equator. You know, and we're used to looking at mid-latitude cyclones over the United States, but they get them over there in Great Britain as well. Because guess what? They are in the westerlies as well. The westerlies go all across the globe. It's not just here in the United States. So this is a well-developed mid-latitude cyclone over the British Isles, moving from west to east within the westerlies. And this one is going to rotate in a counterclockwise fashion because, yep, it's the northern hemisphere. We're going to skip this